All right, so we're going to start today by doing some review of what we discussed last class with our substitution of alcohols. All right, so we got three reactions here. Okay, again, just to be clear, we're talking about substitution. And we're going to compare these reactions to substitute primary alcohols compared to secondary alcohols. All right, given what we discussed last class period, everybody take a second and see if you can't give me the product for these three reactions here. All right, so remember, if we want to substitute out alcohols, that hydroxyl group is a terrible leaving group. So the first thing we got to do is replace it with something that's going to be a good leaving group. And one method that we learned was to replace it with a halogen. So phosphorus tribromide would replace that hydroxyl group with a bromine, a nice good leaving group. So then when I treated that with my nucleophile, and to be clear here, we have sodium acetate, but of course the sodium isn't doing anything. I'm going to replace that with a minus sign. So that's really my nucleophile, my nucleophilic site, that oxygen. And that nucleophile is going to attack, and that leaving group is going to leave all in one step in my mechanism. All right, this is what we called an SN2 mechanism, right? SN2 meaning we have nucleophilic attack and our leaving group leaves all in one shot. All right, all in one step. In fact, both of these reactions here are SN2 reactions. So then my final product, just to be clear, I'll now have that oxygen bonded to my carbon, but it's got that carbonyl group on the other side, those two carbons in that carbonyl group. Creating what we call an ester. This functional group right here is an ester. We'll talk about that towards the end of the course. That's one of those functional groups that we address in this course. But we know how to make it here. All right. So again, both of these steps being that SN2 mechanism, looking specifically at the first one, we said we're not going to worry about our mechanism for these first steps here, but we can show it for our second one, our nucleophile attacks and our leaving group leaves all in one shot. All right, and for this particular primary alcohol, we didn't have any stereochemistry to worry about because by definition there are two hydrogens on this carbon, so it can't be a stereocenter. With secondary alcohols, we do have this stereochemistry that we can worry about. So if we have a stereospecific reactant, right, this would be the R enantiomer of this particular alcohol. We got to worry about what happens when we do our SN2 reactions, because in these SN2 reactions, there's a stereochemistry inversion, right? So in the first step, my wedged bond would be flipped to a dash bond, and then in my second step, it would be flipped back to a wedged bond. So after I do this particular sequence of reactions, I would be left with this stereospecific product. All right, where that sulfur is coming out of the page. Right? We invert and then invert again. If I instead use this other method that we had for creating that good leaving group, that special reagent tosyl chloride does not react at that carbon at all. In fact, it's our oxygen that's going to be reacting with the tosyl chloride, playing the role of the nucleophile. So here we do not have any inversion in our stereochemistry. But when we do our second reaction, our nucleophilic attack, we will have that stereochemical inversion. So instead of having that sulfur coming out of the page at me on a wedged bond, it's going to be pointed into the page on a dashed bond. Right? We had for our first method, we flipped and then flipped it back. In our second one, we had no flip, followed by a flip. All right, so the big difference between these two pathways, if I start out with a stereospecific alcohol, is the stereochemistry of my product. All right, so for my primary alcohol, I don't have to worry about stereochemistry. Best case scenario, for secondary alcohols, we have to keep track of those stereochemical inversions. All right, but what about tertiary alcohols? Okay, specifically in the context of stereochemistry here. So let's get a stereospecific tertiary alcohol. All right, this would again be a specific enantiomer of this molecule here, the R stereoisomer. Okay, so let's treat this with our tosyl chloride. All right, followed by, I'm going to use this as an opportunity to introduce this new nucleophile that's called sodium azide, or really the azide ion here, N3. We'll look at that here in a second. Let's look at this first step. All right, is that tosyl chloride going to change the stereochemistry of this molecule? No, because it does not react at that chiral carbon at all. All it does is glob itself onto that oxygen. And remember, we can kind of simply put that as just TS when we're drawing our mechanisms here. I'm going to make a point here and draw out our full Lewis structure. And remember, why did we put that tosyl group on there? What did that do? Created a good leaving group, right? Okay, so then what happens next, now that we have this really good leaving group, that good leaving group is on a tertiary carbon. And remember, those tertiary carbons can form stable, relatively stable carbocations. So the next step here is just one electron pushing arrow, one bond breaking step here where my leaving group leaves. And that is what we call an SN1 reaction. You don't have nucleophilic attack and your leaving group leaving. You only have that leaving group leaving. Our leaving group leaves. That's the rate limiting step of that reaction. Okay, now I just want to sort of make a point here. We said that this was a good leaving group. Let's look at the structure and try to understand why it's such a good leaving group. When it accepts that pair of electrons, it has that negative charge. Right, but we said our hydroxide was a crap leaving group, and that's an oxygen with a negative charge. So why is this one a good leaving group, even though it has an oxygen with a negative charge? Right, so atoms don't like having negative charge. What's one of the things that can stabilize that charge? That magic R word. Resonance, all right? And we have a lot of different resonance contributors that we can draw that bounces that negative charge around. Not only that, we also have this ring here that can help stabilize that negative charge, right? So we have a lot of different resonance structures that we can draw here that would show that negative charge being bounced around to various sites around this molecule. All right, so that's why this is such a good leaving group here. It's nice and stable with that negative charge. All right, so even though that first step didn't do anything to my stereochemistry, it preserved my stereochemistry. When that carbocation forms, we stop being an sp3 hybridized carbon, we become an sp2 hybridized carbon, and we lose our stereochemistry. My nucleophile could attack from the front, it could attack from the back. I'd get a mixture of both. All right, so there's no more stereochemistry that we have to worry about. So let's finish this off by doing our nucleophilic attack. Importantly, what the heck is this N3 business here? All right, so first of all, if I'm going to get rid of my sodium, replace it with a negative sign, this N3 minus ion is what we're talking about here. All right, this is again called the azide ion. If we want to do our Lewis structure here, we have these three nitrogens all in a row. All right, and those two on the end are double bonded to that nitrogen in the middle. I want you to fill in, these are all our bonds. I want you to fill in missing lone pairs and formal charges. All right, what's missing from this structure here? All right, so we should have gotten with our 2 bonds. We need to complete our Lewis structure here, so we need 2 lone pairs so that everybody's got a full octet. If nitrogen's got 2 bonds and 2 lone pairs, it has that minus formal charge, but what about the one in the middle? It's got that positive formal charge, so that's why I have that net negative charge. And then which one of these nitrogens do we think is our nucleophilic site? The one in the middle or the one on the end? It's got to be the one on the end, right? The one in the middle doesn't have much electron density at all. So I can pick either one of them, they're identical. But that will be my nucleophile attacking that electrophilic carbocation. Cool. So then my final structure here, importantly, I've lost my stereochemistry. Right? I started out with this stereo-specific molecule here. On the other side, I end up getting a mixture of all possible stereoisomer products. So we just represent that with our straight line bonds. Cool. All right, so with primary alcohols, we didn't have to worry about stereochemistry. With secondary alcohols, we had that stereochemical inversion. For tertiary alcohols, we lose our stereochemistry. Because of that carbocation, that intermediate that forms as a result of that SN1 mechanism, we lose our stereochemistry in these reactions. What's up?
Do you lose points if you draw that arrow at the positive sign for carbocation?
No. Well, I mean, so like this,
Yeah.
that's fine. As long as it's pointed at that carbon atom, that's the important part. All right, so now we're going to do our last reaction here. What's called the dehydration of alcohols. All right, just to remind ourselves here, at the very beginning of this chapter, when we started talking about reactions of alcohols, we were talking about hydration of alkenes. That was taking an alkene and adding water to create an alcohol. So if we're going to dehydrate our alcohol, what do we think we're going to make? We're going to pull off a water molecule, and that's going to make what? Hydration, turning alkenes into alcohols. Dehydration, turning alcohols into alkenes. All right, wonderful. So yes, we are going to dehydrate our alcohols to create alkenes. All right? So I'm going to draw a full Lewis structure here to make a point. When we dehydrate this alcohol, we're going to lose the equivalent of a water molecule, creating an alkene, a carbon-carbon double bond. All right, this is again what we call a dehydration reaction. When we went the reverse direction rather, that's what we called a hydration reaction. All right, so we lost this water molecule from our alcohol, creating an alkene, or we can combine a water molecule and an alkene to create an alcohol. And we already learned about these reverse direction reactions, right? These hydration reactions. And now we're talking about these dehydration reactions. So why is the universe allowing us to go both ways in this reaction? Shouldn't one side be more favorable than the other? All right. We already talked about how we can go this way. Now we're saying we can go back the other direction. Why are both of these reactions allowed? All right. So first of all, let's remind ourselves that all the way back in Chem 1B, we discussed this measure of whether or not a reaction was able to happen spontaneously, what we called our delta G of our reaction. Right? And delta G is quite simply a measure of simply does it happen? Right? Negative delta G means that reaction will proceed spontaneously. Positive delta G means it's not going to happen. Right? In fact, the reverse is going to happen. So, why do we get both directions for our reaction here between alcohols, for our alcohols and our alkenes? So we got to remember delta G has these two components. Delta H, our enthalpy, and delta S, our entropy. All right, delta H is what we call enthalpy, or the heat released by that reaction, heat released or absorbed. And this is a result of our bond making and breaking, right? Delta H is a result of bond making and breaking in a chemical reaction. We have to put energy in order to break a chemical bond, but then energy gets released when that new bond is formed, right? That's the delta H of our reaction. And for this particular reaction here, it turns out that the reverse direction, going from alkene to alcohol, is more favorable from an enthalpy standpoint. It's a lot easier to break this carbon-carbon bond than what you get back out when you form these two new bonds, our carbon-oxygen and carbon-hydrogen bond. Right? We got to put very little energy in to break these bonds over here, and we get a lot of energy out when these new bonds form. So our hydration reaction, or rather our delta H, is a measure of how favorable our bond formation is. And our hydration reaction is more enthalpically favorable, more delta H favorable. All right, so then why does this dehydration reaction actually occur? If these bonds are more favorable over here, why are we allowed to push the reaction in this other direction? Because we have this other component of our delta G, our entropy. And remember, entropy is this really weird variable that we threw at you, this really weird thermodynamic variable, right? Bond making and breaking, I think we got a nice, neat mental picture of. Entropy, we were like, yeah, the universe loves randomness. And you're like, what the hell are you talking about? Yeah, there's this energetic push towards randomness in the universe. And everybody's just like, okay, I trust you. So yes, universe loves randomness, right? That's our delta G here. Our delta H rather, geez Louise. Delta S is that energetic push towards randomness. Randomness. And it's entropically favorable to take a big molecule and to break it up into these two small pieces here, right? So when we take something big and we break it into two little pieces, we create more randomness. So dehydration is more favorable from a delta S standpoint. So one of these directions is enthalpically favorable, while the other direction is entropically favorable, and we can tune which direction we want by noting that that entropy term scales with temperature. So the higher the temperature, the more important the entropy is, all right? So at low temperatures, we would get our hydration reaction, but at high temperatures, we would favor that entropy favorable dehydration reaction, all right? So what we're gonna see is heat is gonna be an important component of our dehydration reactions. Okay, so let's take a look at one. right, if we start out with an alcohol, we can create our alkene product, our dehydration product. Like we said, we're going to need heat. We also need a strong acid catalyst like sulfuric acid. And not dilute sulfuric acid, not sulfuric acid in water, but just straight up pure sulfuric acid. All right, let's take a look at our reaction mechanism. All right, so first of all, what do we think? Acidic or basic conditions here for this mechanism? Acidic. That sulfuric acid means we're going to be under acidic conditions. So we got to watch out here. We should see no strong bases. All right, so we're trying to dehydrate this alcohol. We have to break this carbon-oxygen bond here. But as we've discussed at length, that hydroxyl group is a terrible leaving group. So first thing we got to do is convert it to a good leaving group. All right, under acidic conditions, what are we going to do to convert it to a good leaving group? Protonate it, right? If we protonate it, then it will turn it into a water leaving group. So that's exactly what we're going to do. Our acid, because we don't have any water present yet, our acid is going to be that sulfuric acid. So my proton donor here, I'm going to get lazy and draw this condensed form of sulfuric acid rather than the full Lewis structure. But my first step, just like we saw before, convert that oxygen into a good leaving group by protonating it. All right, so everybody take a second to draw me my intermediate. All right, so now I have that protonated 2 hydrogens and a positive charge on that oxygen, making it a good leaving group. All right, and the next step is where our heat plays a very important role. Again, at high temperatures, that more entropically favorable thing of taking this big molecule and breaking it up into these 2 smaller molecules, I'll get my leaving group to pop off here. So we kick off that water molecule. All right, that forms our carbocation intermediate. All right, so what do we know about water here? Let's try to predict what's going to happen here. Water, is it a strong nucleophile? No. Is it a weak nucleophile? Yeah, it's a weak nucleophile. Yeah, it can react with strong electrophiles like our carbocation here. But if it does, if we do a nucleophilic attack, where are we going to go? Right back where we were, right? So indeed, that does happen plenty. These steps are indeed reversible, right? But that's not our productive step forward here. The question is what happens that's going to take us to our alkene product, right? We're trying to get all the way over here. Okay? I want everybody to take a second and try to figure out what we need to do in order to create our alkene product. I want you to think specifically about what bonds need to be formed and what bonds need to be broken in this next step in order for this reaction to occur. And the bonds broken part is the tricky part, all right? I want you to look carefully at this step in our mechanism. Maybe think about implied hydrogens and figure out what bond needs to be broken in order for this reaction to occur, all right? What new bonds need to be formed, what old bonds need to be broken. Take a second and see if we can't figure that out looking at this step in our mechanism. All right, what is it? What needs to be broken? Carbon-hydrogen bond, right? So if we look over here, we look carefully at our implied hydrogens. We have 3 of them over here on my carbocation, but I only have 2 of them up here on my sp2 hybridized carbon. So one of them's got to go, all right? So that's what we're going to do in our mechanism. We got to show our bond breaking, all right, our old bonds breaking and our new bonds forming, okay? In order to have this hydrogen removed, in order to break this bond here, we need something that accepts a hydrogen, what we call a base. But we're not allowed to use any strong bases. So what base do we think we're going to use in this mechanism? We could do our conjugate base. There's actually an even better one out here, all right? And that is the water molecule itself. Right? We can use a weak base like water. And so that's what we're going to do. We're going to grab that proton. All right, if you reformed your sulfuric acid catalyst, I don't think that's the worst thing in the world. But truthfully speaking, if you looked up the pKa's and such, the water is a better base. All right, but now we got to think carefully about our bond that formed, which was obviously this new carbon-carbon pi bond. Where did that pair of electrons come from? The electrons that we got between that carbon hydrogen bond, right? So this is now a bond breaking and formation arrow, all in one shot. Our carbon hydrogen bond breaks and our new carbon carbon pi bond forms in order to get our alkene product here. Okay, cool. So we have this reaction mechanism where we have this carbocation intermediate. And there's something that we always say that when a reaction has a carbocation intermediate, we got to be careful. What do we got to watch out for? We got to watch out for those shifts, all right? Now, I will tell you that if you do this reaction in the lab, there are absolutely hydride shifts that occur. In fact, because of the high temperatures, that carbocation bounces around all over the frickin' place, all right? But for the sake of our sanity and this course, we're going to make our lives a little bit easier, and we're going to say that for these particular reactions, we're going to go ahead and ignore those shifts. All right? Even though they do occur. It would make our life a nightmare to try to account for all of those pieces of the puzzle. All right? We're going to see. It's already going to be a little tricky enough trying to figure out what our products are for these reactions. We don't need to make our lives more difficult. We're going to note, if we are in the lab, we will expect to see hydride shifts, but for the purposes of our pencil and paper organic chemistry, we're going to ignore them. All right? Cool. Okay. So why do I say that we already got a little bit of a problem on our hands? So in this case, we only have that one product, but as soon as we make things even a little bit more difficult, let's take a 4-carbon alcohol. All right, we're going to call this our predicting dehydration products. So I'm going to take this alcohol, I'm going to again add that concentrated sulfuric acid and heat. But I'm not just going to get one product out of this, I'm going to get multiple products. All right, so why is that? Well, let's look carefully. My carbon-carbon double bond that formed here was between which two carbons in my alcohol? Certainly the one that was bonded to that oxygen, but also its neighbor was involved in that reaction as well, right? That neighbor had to lose a hydrogen in order for that carbon-carbon double bond to form. Well, in this case, it wouldn't matter which neighbor I chose. I would get my same product. But here, it is going to matter, right? I could have my dehydration happen over here with my carbon on the left, or I could happen over here with my carbon on the right, and that would give me two distinct alkene products. All right, so everybody take a second. Let's draw our distinct alkene products here that we would get depending on which direction our alcohol dehydrates in. So obviously my blue carbon is going to be sp2 hybridized, but which of its neighbors is that double bond formed between? Again, I could get two possible products. One, if it forms over here between the blue and the red carbon, and another if it forms over here between the blue and the orange carbon. Right? Two distinct alkene products. Okay? So we have these different directions in which this molecule can dehydrate, leading to these two different products. I know they're two distinct products because they have different names, right? What would the name of this one be? One butene. And what about the name of this one? Two butene. All right, but it's even more complicated than that, because this isn't just 2-butene. You'd put in 2-butene, you'd hit enter, and SmartWorks would be like, bam, wrong. Why? What are we forgetting here? Stereochemistry. This isn't just 2-butene. This is specifically the E stereoisomer of 2-butene. All right? We're going to get yet another product, our other stereoisomer, our Z 2-butene. All right, everybody take a second. Draw in that third product for me. So now I'll have those two methyl groups on Z-zame-zide, my Z stereoisomer. Okay, so everybody's looking over here at our alcohol on the left and our Z2-butene and be like, what the heck's going on, right? This does not look like this structure at all, okay? Well, let's remember, this molecule isn't frozen in this rotational state. It's constantly rotating about all of its single bonds. So I could draw this exact same molecule in a different rotational state, where now that carbon's pointed down. This is not a distinct molecule at all. All I've done is rotate about a single bond. So it's going between these two conformations all the time, right? So sometimes it's in this conformation forming our E stereoisomer. Sometimes it's in this rotational state forming our Z stereoisomer. We will always get both possible stereoisomers. We can note we're specifically talking about EZ now with our double bonds. So then the last thing, we predicted our 3 products here. The last thing I could do is ask you what our major product will be. Okay? And if I'm thinking about my major product here, I'm thinking about which one of these is the most stable of the 3, the lowest energy. All right? What am I going to be looking at when I'm thinking about stability? So stereochemistry is one, and the other one is? So conjugation would be great. Absolutely. If there was another double bond in this molecule, if there was a double bond over here, for example, that would definitely influence what our product is. But these aren't dienes, right? So I don't have that conjugated, cumulated, isolated. That was our first level of stability. What was the one right after that, though? The substitution. The mono, the di, tri, tetra business. The degree of substitution is what's going to dictate our stability. And then after that, the third factor was that stereochemistry. So absolutely, we're going to consider these 3 things. We get to nix the first one because we don't have a diene at all. But we do want to think about our degree of substitution. So which one of these 3 am I going to nix as a minor product because of that degree of substitution? The 1. This one's definitely going to be a minor product. Now these ones are tied for substitution, so I have to start thinking about that next level down, stereochemistry. And what's more stable, having these 2 methyl groups on opposite sides or on the same side? Opposite. They want to be on as far apart as possible, right? Steric hindrance, we want to be as far apart as possible. So my major product here is that E2-butene. The other 2 will be produced in minor amounts. All right, let's do one more here. All right, so let's predict our products. Importantly, we know that this carbon bonded to my oxygen is going to be part of my alkene, my carbon-carbon double bond. But we have these 2 neighbors to choose from. So everybody take a second and dehydrate our alcohol to the left and to the right. So I'm going to do one product where I dehydrate on the left. And I'm going to do another product where I dehydrate on the right. All right, and am I done? Okay, so we got to be careful because as we said, we're always going to get both possible easy stereoisomers. If I look here, what I drew for my first one was the E stereoisomer. No, it isn't. Sorry. Damn. All right. I wanted to make a point here. Well, whatever. This is fine. This one doesn't have any stereochemistry. So I don't have to worry about drawing a second product over here. How do I know that this one doesn't have any stereochemistry? We got 2 identical groups, which means that I messed up in the example that I gave. But it doesn't matter because we can still prove a point down here, which is that this one is my, which one, E or Z? Here's my high priority group, So this one is my E stereoisomer. So I do have to make sure to draw my Z stereoisomer. All right, where I'm going to take one group and put it on the opposite side. So I'm going to take that carbon, that methyl group on my orange carbon, point it up. And then if I'm going to ask you which one of these is the major product, everybody take a second and decide. What do we got? A, B, or C? A, my more substituted alkene here, my more substituted carbon-carbon double bond. This is my major product. Okay, I just want to note I had kind of intended to put one extra carbon on here just to make a point that this would indeed have 4 potential products. All right, so just to kind of have in our notes here, we're not always going to get 3. That was just because of the examples that I picked. This one would have these 4 potential products. Well, 4 products. And I could ask you which one was major and which ones were minor. Okay. I'm going to leave it for y'all to figure out what those 4 are. Suffice it to say, you're going to look, figure out whether you have the E isomer, the Z isomer, or there's no stereochemistry. If there is stereochemistry, you have to make sure to draw its counterpart. Cool. All right, done with alcohols. Enjoy your weekend. We'll pick up with our next chapter next class.